Now we're on section 6, forms and false work, page 631 of the presentation slide. Forms and false work used to be, when it was a 3-week course, this was a full day. And actually did a lot of calculations of how do I know what my spacing of my 2x8 should be for between beams, or what size of plywood do I need, or I'm building forms. But things have changed. That was 20 years ago. There was still inspectors were doing a lot of those calculations to verify that forms and false work and stuff was adequate. But now we teach enough so that you guys understand some of the things that go into designing and constructing forms and false work. To know what kind of things are important to look at, to know what kind of things the contractor is responsible for, what kind of things MnDOT or the owner should check, and so on. We pared it down from a full day to we're going to have a little over an hour, I guess. We'll have for this presentation. So the final shape and form of cast-in-place concrete, and really the precast concrete as well, is directly dependent on the forms and the false work that's used. So we'll look at the terminology of what does this mean. So the goals, as I mentioned, this used to be a full day class where they did a lot more calculations. So the goals aren't that we're going to calculate stuff, but to understand what goes into forms, what goes into false work, what makes a bridge stand up, and so forth. So we'll talk about some examples, some resources for reviewing. There's a lot of references in here to the bridge construction manual. It's not our BCIC class manual, page 6.1, but on the back there's one copy of the bridge construction manual. And there's a whole section in there on forms and false work. And that is a good go-to. You can get a copy of that bridge construction manual online. So it's a very good resource. It's getting a bit dated. MnDOT has been looking to update it. I actually rewrote the part of the piling one here a couple of months ago. So we may see that one changed. I guess once I'm on the topic, for future classes, the goal is to not have a separate bridge construction manual from our bridge construction inspector course manual, but to combine them into one, so you'd have more like one document. But we'll see what some of those resources are. Reviewing false work plans, what kind of things you look for. Inspection, what do you guys as inspectors need to do when there's false work? And then things like stripping the false work. There are some requirements in the spec we'll talk about some of those. So what are forms? And it's a temporary structure to mold or retain the plastic or concrete shape. And so all that's meaning is if we have a pier cap and it's supposed to be 4 feet wide and 6 feet deep and 100 feet long in our bridge's case, we want to have forms that will retain that. When we pour the uncured concrete in there, it's going to be to that form. It's going to also provide the proper clearance from our rebar and all the things like that. But it must have enough strength to resist the fluid pressure exerted by plastic concrete and any other pressures generated by vibration. Uncured or wet concrete has a lot of force that's trying to get out. I don't know, has anybody been around when you see a form failure of anything? You blow out and the concrete is all over the place. Yeah. So if you just have a little form and you tack a couple of nails in there, it's not going to last very well. And so there needs to be a thought process to withstand that. The design plans, bridge design plans, do not tell the contractor how to construct the forms. Bridge plans only say build it to a given dimension and so forth. So it's up to the contractor to design the forms, and then the falsework we'll get to in a few minutes. They also have to then account for any additional pressure from screeds, from workers, everything has to be supported. So we're going to build a wall. This little simple example is how forms and falsework work together. So we start with a footing, we have a little keyway in there. We put up a couple of walls, might be good to go. If I stand here and hold this form, maybe it'll be good. I mean, literally, if you then start pouring concrete in this kind of a configuration where you're just kind of balancing forms on here, what's going to happen? Fall right over. Obviously, this isn't going to work. This form is necessary, but it has to stay in the right position. So we'll add something like some studs that will last, that will be put in there. Okay, or better, maybe if we nail this down, maybe you have a chance of holding that concrete for a little while anyway. But that's still probably not going to do it, right? So let's put in some additional things. Now we're going to start to spread load, not only from this one member, but we're going to go out the side. We're going to tie all this stuff together. Still not very stable. This is still a wall that's going to go like that. Okay, now what? Let's tie it together. And so we have a few samples of things. So this is, for instance, something that would be used to tie a couple of forms together. So the wall forms would be here. These little cones, we'll talk about that in a bit. Would be able to, after you break off, these things have a weakened plane, and so they can break them off once the concrete is cured. And you'd be left then with a little cone that you fill up. But that's similar to what's going on right there. And so then maybe we have some additional blocking that comes in, some plates, and now we should be ready to add concrete. And so put some chamfer strips in there maybe to soften the edges, and we're good to go. So here is just looking at some of the things that we have. So things like over here, there's a tie plate, or here's a little different example, different ways to put plates that you can use to connect your forms. But there's tie plates, there's sheathing. We're gonna talk more about sheathing and things like that. So that's forms. What about falseworks? I've been throwing around the terms forms and falsework. Falsework is a little bit different than forms. Sometimes they're the same. We're going to see that like on pier caps. But falsework is something that's underneath all of this load, and it's keeping whatever load is getting constructed in the proper orientation until the concrete is cured and is adequate to withstand the load. So it's temporary construction work used to support the permanent structure until it becomes self-supporting. So falsework would include steel or timber beams, girders, columns, proprietary equipment, shoring frames, and different things like that. Probably one of the larger jobs I've ever been on as far as falsework was the St. Croix. There was a huge amount also on 35W. There was a lot on other big bridges, Lakotas, and so forth, where there is some cast-in-place box girder kind of work. But on St. Croix, there was 10 million pounds of structural steel for falsework. No pay item. That's just, it's what the contractor has to do. So 10 million pounds of structural steel had to be incorporated in their bid for whatever our items were for casting place concrete boxes. But a huge number, huge piles, pile bents. I think we got a couple pictures of it in this presentation. But it can include, falsework can include a lot of these kind of things. And oftentimes it'll be a bent like this. This is showing a case of timber bent. So some timber caps, some pile caps, and again, it could be any material. It could be steel. Some bracing to make sure that things don't go sideways on you. So that's just kind of a picture of what we have. Here's another one. Slab spans. We mentioned that on day one, that a slab span doesn't have a separate beam, but it's a thickened slab. So oftentimes, say 20 inches. It'd be a 20-inch thick slab span. So it's not just a deck, but it's a slab with structural. And it's supported during construction by something like this, where here's some steel girders or beams that are going from abutment to pier, and pier to pier, pier to abutment, or whatever, to accommodate. So there are some applications where something is both a form and a falsework, and so sometimes you just call it a form work. But a pier cap is one of those. So here's a pier elevation, and we're trying to cast this pier cap. And we've already cast the columns, and so to withhold that load, we're going to put a friction collar here. Sometimes there's some through bolts that go through the concrete and hold up some kind of a bracket that's going to then hold up a beam, that's then going to hold up these stringers, that's then going to hold up the concrete that's here. So I mentioned the other day about load path. So any of this stuff, essentially the engineer is looking at what is the load path. So we're going to put a whole bunch of concrete out here at 150 pounds per cubic foot. It's going to come down here, so this piece of concrete says I'm going to come here and I want to get supported, and so I'm going to go through the plywood, through the stringers, into the beam, over here through the collar, and the collar through friction is going to send the load down here, down to the ground. So load path. So what we often look at, and I'm going to point out section AA. So section AA, again, we're cutting through the pier cap, and we're turning, and we're going to look like we're looking right through the pier cap. So on this sheet, then it shows that's what we would have done. Now we're looking at what we see. So in this case, the contractor said, okay, we have an HP 12 by 53 on top of a friction collar, and there's probably going to be some kind of a bracket that looks like a kind of an odd configuration. And then we put the rest of our formwork up here, and some kind of little stringers, 2x6s that are there. So that's an example of kind of a combined function. This says typical forms and falsework. I don't know that this is really typical. It's more on some of our bigger projects, but using jump forms, that's what these are called. On St. Croix, we went up like 15 to 20 feet at a time, going up towers that were, the pylons were, below the deck was about 80 feet, above the deck was about 65 feet, and so you have several different pours that are going on, but literally they are able to lift themselves up, and tie rebar above it and go on. So those are things that we have there. Additional functions here is an abutment. Sometimes, even though we put our forms here, it's still not very stable. So oftentimes when we some type of a brace here that will go into a concrete block. So the contractor will cast concrete into a block like that. Sometimes it'll be onto maybe a pile that's driven in. Different ways to do that, but again, essentially to keep some overturn. It's always important to make sure that we are plumb. So I remember one of my jobs when I was a grad engineer on that Lake Avenue project was I would have to go look at the level at that time, or the survey equipment, and turn the angle and make sure that we're still centered. And so, through surveying, through whatever methods, we want to make sure that things aren't starting to shift off one direction or another. So forming the abutment, here's some pictures. This looks like the Rochelle Pit again, the bridge there. So some pretty big abutment pours. This one, you can see these big vertical, for their bearings. They had some big anchor rods that went down in there. But again, forming and rebar placement, things like that. So a little more closer up view. Our forms can be steel, they can be timber, wood, different materials that we use. Sometimes we hear of the term shoring, and that can have a couple different things. It can be horizontal, vertical, it can be inclined. And today we're going to say it's really a part of falsework. It's a way of falsework that we can use. So there's several different techniques that we can use for shoring, but it's a process of supporting in a building or a structure or trench with shores. So bridges aren't the only place that we use that, but this is what we have. So shoring can be towers. So this first example is a shoring tower. So it's this kind of a configuration that with some X bracing to make sure everything is. And so this is a steel box, a steel tub. And to hold those splice locations in the correct location, they had to provide shoring towers. And so that's what's depicted here. Shoring can also be, as we saw the other day, a cofferdam. So this can also be called shoring. Keep the area dry so that we can avoid the dry. In 2401 spec, so there's a lot of information in here. So starting on page 347. So familiarize yourself with that part. And it's going to give us a lot of details. We'll highlight some of them here in these slides, but not all. And so under this part of the spec, let's first talk about design of falsework and forms. So on page 347, down at the bottom, B2, submit detailed plans for falsework and forms to the engineer. So right there, it means that the contractor is responsible. He or she has to give how are they going to do this work. And then it goes on to say, provide falsework members to safely carry the following load. This doesn't say anything about the bridge plans have falsework in it. It doesn't say anything about MnDOT engineer designing the falsework for the contractor. It says, contractor, you are responsible. And so we then want to design to carry that fire enforcement. And also provide credible information regarding the performance of the proposed falsework. And we need to do, if there's not sufficient performance data, we need to do full scale test. I haven't really seen, I saw that one time really to do a test of what they had, so it's not very often instituted. But if there's something that they want, okay, here's a new concept, what we're going to do. If there's not sufficient info, maybe they need to do that. So the contractor is responsible and to verify to the engineer's satisfaction the strength and safety of any design. So there's been a lot of requirements in here, and let's move on to the next one, where the contractor must submit detailed plans for falsework form, and he or she must verify the engineer's satisfaction the strength and safety of any design. Contractor's responsibility. Another key point is this third bullet. Falsework designer must review in person, meaning in person, in the field, of what that design was and approve that the installed falsework meets the intended design of the falsework plan. So I mentioned the other day that I'm going to talk about a time when a bridge construction supervisor, Leon Lilly, I don't know if any of you ever worked with Leon, great inspector. He was in charge of the Lake Street Bridge. It's a concrete, cast in place concrete arch. A lot of false work. They're out there casting on one of the arch ribs. A lot of weight, a lot of concrete trucks out there. And all of a sudden, everybody heard something. Something moved, they could maybe feel something. And everybody's wondering what to do. And Leon had the courage to say something is wrong here, everybody off the bridge. He didn't care what, there's going to be a cold joint in the concrete at the minimum. Everybody got off the bridge, and then a half hour, maybe an hour later, everything clapped. Boom, down it went. There were a couple of contractor people who were up climbing on the falsework. One person unfortunately lost his life. Another person made it. But I still give credit to Leon's actions, that they probably saved countless lives. And if they had kept on pouring, and you got inspectors out there crawling around, you got all kinds of contractors, people finishing concrete and whatever, it could have really been bad. After that incident, MnDOT toughened our specs, and we require the falsework designer to come on site. So like on St. Croix, the falsework designer was out there probably 8 or 10 or maybe even 12 times at all the different spots of falsework. And the reason the Lake Street collapsed is there was a bunch of little members coming in, load, transfer coming down. But everything came down through a 36-inch deep beam. And steel beams can be very good in bending. They can be good in tension. They can be good in shear, but in this case, a lot of load was coming right down through that little member, and there was not enough shear stiffeners to stiffen up that web, and so everything collapsed from that member. And so we think, just as engineers, if we had been out there, if an engineer had really, the guy that designed it, had said, okay, load path coming down, well, look at this, load path is coming through this little member and there's no stiffeners. It would have been a fix that you could have welded a stiffener on. You could have even put timber blocking as a stiffener. But I recite that for this reason, that don't take this part lightly. That the falsework designer has to come out and approve in writing. You know, visit the site, approve in writing that yes, this is what I intended. So if the contractor is responsible for the design and the construction of falsework forms, why do we then need to concern ourselves? with falsework forms? Well, we want to have a basic understanding. We want to be able to say, like Leon, something is going wrong here. And there's great expertise in this room. You guys have great minds, so you are able to look and be able to say, something doesn't quite look right. Maybe it calculates out perfect, but it's good to raise those questions. So we need to know where to look, what kind of things. And to do that, we need to have a basic knowledge of materials. Some things are wood-based, some things are metal, some things are manufactured, some things are concrete, not necessarily concrete for falsework. We need to understand how structural systems work. We need to understand load path, load transfer, things like that. What are the loads and what are the failure modes? So things like that, shear bearing failure, are things that we want to be well aware of. So what do our specs say? So we already said we opened at page 346 of our specs, 347. Construction requirements are there. Steel Bridge also has some things. 388 to 390, talking about falsework and how things work. So it describes what the forms in falsework must be. It doesn't give details. There is then section 2403 for wood construction. So there are members that fit into that, and they're applicable to timber falsework elements. So you all have the spec book, but if you need, there's a link. So I mentioned the bridge construction manual. There is one manual back in the back if you ever want to take a look at it, but section 200 deals with falsework and forms. It's fairly detailed. There's actually colored pictures in it. At least I think that one was copied in color, and it has some good information. The Lake Superior website has a link also to that, or you can get to the link to the bridge office website. Yeah, here's the link to the bridge office website. Instruction manual shown there. And in color. Okay, so let's take a look at some real-world examples. This is something we don't use in Minnesota. It's stay-in-place forms at the bottom of a deck. The reason we don't is it's been so difficult to be able to inspect what the concrete is doing. I don't know, maybe someday we'll see more of that. Right now, they're not allowed. But it's a lot of labor for the contractor to remove the underdeck forms. And so if there was a way that they could just keep something in place, it would save a fair amount of money. So some of the material that we have is the falsework piling, lumber, the sheathing we're talking about, some form landings, rolled and proprietary shapes. So everything must have an approved method for determining and certifying this term allowable working stress or safe load. So essentially, what is the capacity that we have? And they can use used material, provided it's in good condition. The contractor's plan has to clearly indicate what is the structural grade used. And this comes into to play for structural steel. The two main grades we have are 36 and 50. That means KSI, kips per square inch. 36 KSI is weaker than 50 KSI. And so we need to be able to verify if they call out 50 KSI material, is that indeed what we have? If not, they'd have to take a test, shoot on, and untreated timber piling, you might say, boy, that looks like that's never going to work for anything, but it can work for falsework. It wouldn't be something we'd use in our end of the 2-way bridge. So here's just a picture of using some untreated timber for some false work. Here, this one, so it looks like a pretty large pier cap in this case. You see a concrete column, and then in between there is a steel with the H bent there. So adding some piles there. This is not St. Croix, but the same concept was used on St. Croix. It's something that's pretty ingenious, and the first time I saw it, I said, what do we have here? This is falsework, so there's some piles driven in the ground, maybe a little member coming this way. And then we have this little box that goes onto some kind of shoring towers up above. This is called a sand jack. They literally fill this thing up with sand. It's pretty ingenious because then you open up this little valve, and if you need to lower your falsework, it'll come on down. Now that doesn't help you if you need to raise it, but usually there's screw jacks or something that you can raise it. But where this is really beneficial is you've cast the concrete now, you've got this huge load sitting on top. How are we going to get that falsework out? You open up this little valve, sand comes out, falsework drops, and it's easier to remove. So, pretty ingenious, and I've seen it on quite a few, including the St. Croix. So slab spans are a type of bridge that gets built a lot, especially on the local system, smaller bridges, some on the MnDOT system. But oftentimes you're going to need, not often, you will need some substantial falsework to hold the loads up. So this is showing a configuration that they have something attached to this pier wall, maybe some kind of a through bolt, a bracket that's supporting then these girders that are going this way, which in turn are supporting these beams or girders going this way, which in turn are supporting these, whatever those little members are, which in turn is supporting all the concrete load of the deck. So more pictures of that, though you can see the through bolt configuration. So different than the friction collar we showed earlier, but just a way to connect and provide bearing. Sometimes they go down to the footing. So this is a case where you just put some vertical elements either down to the footing or perhaps this one was actually just bolted through the back wall of the abutment or the pier in this case. Again, forming underneath, some pile bent, temporary. This is, I keep this in here, probably the one and only. You win the prize for the most shims ever in a bridge construction project. But be looking for that, and this would be a perfect case for if the falsework designer comes out, he or she sign off, make sure you point out, okay, I've seen these areas, make sure you look at them. Are you okay with 15 2x4s stacked on top of each other as part of your falsework? So regardless of the type of falsework piling used, contractor has to provide evidence that piles are sufficient. So they need to be running a PDA. They need to be running the MPF 12 formula for their piles. So make sure that those piles are sufficient and they don't settle under the load. So we've got a few slides in that talk about some of our wood and timber elements. So obviously hardwoods are the broad flat leaf trees, the ash, elm, oak, so forth. They get used sometimes, but more often we have some of the softwoods, the pine, the fir, get used as some of the materials for our falsework and our forming. So in 2403, there are some descriptions there. It consists of constructing the wood structures or portion of the structures made of timber and lumber. And so then the materials talk about what are the structural woods, what's the component grading, and it makes a reference to 3426, and that would be in the Division 3 part of the spec. So all of the lumber has to be sorted and based on strength, and they're called stress grade. So we don't have to be experts in lumber grading rules, but know some of the basics. And you know, nowadays you can always find a lot of information, and the bridge construction manual has some. But what do all of the little symbols that are stamped on wood mean? Wood always has some natural imperfections, but we just want to limit them. We don't want to have all kinds of knots that all of a sudden that piece of timber is going to be weak. And so, you know, just keep an eye on that. Working stresses have to be within the range. They can't exceed the stresses required in the bridge construction manual or in any of the contractor's drawings. So here's just a grade stamp. So there's certification marks. There's what's the moisture content, what's the species of wood, and especially, you know, if there's a requirement to be a more dense wood, an oak or something, and they come out with a soft pine, you know, it's not going to fly. So make sure we understand what we. So sheathing is something that gets used a lot, and it can be used. The bridge sheathing, and it'll provide, and there's plywood for form sheathing. It has to meet certain requirements, which we'll see that on the next slide. So this is in 2401, 3B01D, and it talks then about what does the plywood have to be. So B1D is the bottom of page 346 onto 347. And so it says it has to be at least 5 plies, and it has to be at least 3/4 of an inch. And it needs to meet, as it says here, the ply form exterior grade with sanded or overlaid surfaces. And so, you know, you don't come with some of the cheapest plywood you can find at the store, but it has to meet these requirements. They do allow, the specs do allow, if you have tight radiuses, that you can provide plywood sheathing thinner than 3/4 inch. I mentioned St. Croix had a bunch of curve in it, and so we had some pretty tight curves at the bottom of the box girder, and so they had, it was like 1/4 inch, maybe even an 1/8 inch plywood, just to be able to make that curve, obviously supported members behind it. So some pictures of where sheathing is used. So here's a picture on the left at an expansion joint, how the sheathing would look. Here's on the deck overhang, sheathing looking there. Here on a wing wall, passing out the wing wall, a sheathing where, and plywood is a term that we would typically use, but ply form sheathing is the proper term. So what is ply form? It's panels that are manufactured to be reused multiple times. That doesn't mean they can bang it up and so forth, but it means that keep it in good condition and it can be reused. So the plywood industry does, it's a special product called ply form, and it's proprietary, and it can only be from this APA, Engineered Wood Association. But at any rate, it's a plywood that can withstand the pressures, it can withstand the moisture of concrete. When we look at plywood or ply form, it always has maybe I shouldn't say always, but this material has an odd number of plies, either 3 or 5. And the one that's going to be on the top and the bottom, the direction of the grain is the strong direction. So you typically want to see that ply form, if you're going from a girder to girder, it should be running with the grain of that plywood from girder to girder. That's the strong direction. And so this little depiction down here, blown up. So the strong direction, you're running perpendicular to your load support. The weak direction would be here. So you just have more plies running in the strong direction. So here's just some more information. Class 2 is the weakest grade of ply form that's actually produced. So to be aware of some of the things that we have there. Those of you who have done a bit of construction may have come across some of these kind of things, the SCL, the glue lams, the LVLs, PSL. It's all kind of manufactured wood. So instead of just taking a tree and making a 3-inch by 12-inch piece, they take a bunch of smaller pieces, glue them together, and make the larger element. So the same thing with some of the ply forms that are put together. So those can be used. They're certainly fine. There's whole strength tables that, say the LVL people have tables that show what is the strength of their material. So rolled steel shapes are often used. So this one is marked out really nice. We know exactly what they are. It's 14 by 132s. So we know that's perfect, provided the strength is the correct strength that has been required. If you don't know what a size of beam is, there's no, it's not like this where it's marked on there W14 by 132. There are books. So this is out of the Steel AISC manual that you can measure what we have. So all of these little things, it has little dimensions. So like here, a D is the overall depth of that beam. So there's going to be a depth of the beam. And so if we measured it and it's whatever that says, 14.66, we can say, okay, well, we're probably going to be that beam, or at least we're in the zone. Same thing with the web. So there's a thickness of the web, TW here somewhere. Same thing with the flanges. There's a width of the flange, this D sub F, and the thickness of the flange. So from that you can determine what the size is. So that would be something you as the inspector, if they don't come out there with the size stamped on it, if they do, you might verify, take a couple of those dimensions, make sure it's correct. So here's just a little thinking exercise. So a contractor's foreman, they're out there building, and they request a change to change a W30 by 150 beam, which is the top line there, to a W33 by 152 they have in their storage yard. He said the beams are heavier, so it'll work fine. Does this seem reasonable? What would you do? So the higher numbers are all highlighted. So they want to use the bottom line there, change from what's in the drawings. What would you do? Tend to say, yep, that's okay. It's heavier. Call the engineer, talk to him about it.
Yeah, because your price is going to definitely change, so your elevations are not going to be correct.
And you can modify the elevation, you just start them up. So I wouldn't be concerned about that. But call the engineer is exactly right, but what else might we see? Anybody familiar with structural properties?
The modulus and moment of inertia can cause problems.
Moment of inertia could cause problems. That is a big factor in deflection. This S sub X is a big factor in our bending stress. And so even though our weight is more, that particular beam, the 33 by 152, it's going to have more deflection because this number is less, and it's going to have a little bit higher stress because this S sub x is a little bit less. Okay, will it work? It might, but that's where exactly you would call the engineer. Say, okay, Mr. Engineer, it's your responsibility. You say, yeah, go ahead and use it. Okay, if they say yes, then fine. We'd be okay. They said, yep, the deflection is going to be fine for what we have. The strength, I was way over. I didn't need that much bending strength. So those are all things. So the weight and flange thicknesses are all heavier, but the section modulus is less, moment of inertia is less. And so get the falsework designer to sign off if they want to use that. Form lining, I'm not going to do much here because Melissa's going to come in on Friday and talk more about form lining, but when we are considering forms and falsework, we have to consider the thickness of the form lining. So form lining material looks something on this order, and it's 3 or 4 inches thick, and so they have to be able to accommodate that in the thickness of their, or in the width of their forms. These get attached to the face of the forms and constructed. So, you know, there's a lot of different form liner things that we use nowadays. A lot of things that are pretty impressive. But what the forming has to do is accommodate that, and also accommodate then whatever clear cover we need, especially if there's any bone rustication and things like that. So form lining, any people ever, you guys are construction, so anybody ever ask you how they built those stones on that pier column and stuff? So I've had people say, wow, I didn't know that they still put actual stone, but they do such a great job nowadays with some of the surface finishing and the texturing that people think it's actual stones, but it's cast concrete and then it's stained and painted and whatever. So. Talk a little bit more about proprietary things like wall form panels or circular column forms. So these are things that you can buy from the supplier, things like that. So we'll talk about some of them. Friction collars, I had a picture up earlier on friction collars, and so that is something that that do get used from time to time. Literally, friction means that it's using friction. There's no through bolts going through that, but it's using the friction by, you tighten it up, and then the friction between the surface of that metal with the concrete is what is holding up the material. Steel joist hangers. This has been a big thing invented by a guy in Minnesota. Board hangers. So invented by Mr. Board. This is something that gets used on bridge decks. This will hang on the top flange of the beam or the bridge, and then the stringer would go in here, and then we'll talk about stool heights next week. But if we need to put that stringer up, they screw it up or screw it down accordingly, and then we'll set the height depending on where it needs to be. This has been very, very good tool. We'll talk about how sometimes you get failures when this thing kicks out, and so they would have a little kicker from here to the web. So that is a product that it's been I don't know, you see it on just about every bridge project. So, and this, I guess here's where we talk about the joist hanger failure. So here they were casting along, and all of a sudden the forms fell. Big hole in the deck. What do we do? So we had to make make a determination, well, we had to exit that core and, cast it at a later date. So what do we think happened? Here's a picture of shortly after that collapse on the adjacent part. So what do you think happened? Who can give me some reasons of what happened? Who has some thoughts?
Kicked in.
It's Cole, you had something in the back.
Yeah, it looks like they probably didn't have enough of the supports going over to the well, like you said. They have a couple there, but
Yeah.
probably not enough.
Yeah, so you got a couple little pieces here, but did they have them in, or did all the rest fall out, or what? So that's one thing. There's another thing that right up where these stringers kind of butt up, there can be a little gap, and if that gap doesn't get filled in with plywood, it gives it a little bit more room to move. Plus, then the deflection of those girders it'll cause some movement. So those are kind of the things that happen.
Do you have a two-piece joist there? Because it looks like they've got a little spliced block over connecting the two pieces of the joist.
I'm sure it's not, but it's kind of a weird picture, isn't it? So you're looking at this.
Yeah.
It's right here. I've never noticed that before, but
Looks like they tried to make it thicker.
it is. It's like
Because
they had.
the ones farther down don't have that.
Yeah. So it could be.
It didn't work.
Yeah. So I'm not sure. It is kind of a weird look there.
Yeah.
But yeah, it's like I ran out of 2x10, so I'm going to use a 2x6 and a 2x4 and scale them together or something. I don't know. I've never paid attention to that before. Okay, O-ring brackets. So these, to me, it's one of the most remarkable things of deck forming. You go out there before they cast concrete, and sometimes there's really some weird-looking geometrics. But sure enough, they cast the concrete, and the deflection comes out. How do they figure it out? It's all from the manufacturer's literature. That it'll say, we anticipate if you have X load on there, it's going to come down Y inches. So stay in place, again, we don't use them much. We have tried even things like thin, roughly 4-inch panels on some of the bridges on 610. We got a lot of reflective cracking. On the 4-inch panel, we then came with like a 5-inch deck on top, but it reflected through pretty strongly. So, but those are stay-in-place forms. Here's some pictures of shoring, and Andy actually had this similar photo, same bridge anyway. And so shoring can be used to hold up the soils as the abutment is then constructed. This oftentimes, this looks like it could be a staged construction where you build half of the bridge over here, and I'm not sure why they would need it, but then you come and build the other half. So metal scaffolding, these shoring towers, it's proprietary, so each one would say it's, each leg can withstand X kips or something. Be able to go on like that. Here's one that's a lesson learned. This is one of the box girders. As you go 610 going west from here, you cross the river, and there's a couple of box girders. This detail, and I'll blow it up here, but this is the detail in the plan, and especially this one right here. When we blow up that detail, look at what that is. Right now it looks like it's maybe a solid black line. And so we also then have bars that are crossing, And so this bar crosses and goes up, and it goes up the left side, this one goes up the right side. Everything crosses here. There's no bars on the outside of that pier. Who might have a reason to think, why would we just cross the bars at the top of the footing to go into the column, and there's none on the outside? Okay. It's load transfer, and more than load transfer, it's... So what we're trying to do, everything up on the top here is tied into the superstructure. So there's no expansion that's allowed up at that point. But we all know temperature is going to affect the bridge. This was, I don't even remember, was it 2 columns plus abutment? So each of these piers, as it gets cold, it's going to contract. As it gets warm, it's going to expand. That pier column has to move. And the way the engineer made it move is to make essentially a hinge right down here. So a little hinge. Odd detail. We don't see that very often, but it was used on a couple of these bridges in their presentation. So the reason for that is it's a hinge joint. It's to allow a movement, so that pier then will stay fixed on the footing, but it enables it to move. Well, to move, you have to have something that's compressible. So this picture here shows compressible material all the way around. And so then, where should the bit felt be placed? So this detail up here shows this all the way through, or so it appears. So I get out to the site just for a site visit. They didn't call me out. And I see bit felt everywhere under here except where the actual rebars were. So what's the load path? It's coming down through concrete, and then it's going to go through bit felt, and then it's going to go into the concrete footing. And so what's going to happen? The load is going to be try to compress that bit felt, or it's going to try to compress those bars. The bars will try to build. So the intent of the design was there would be some zone here of, whatever, a foot wide or something, that the concrete would be able to come down and it'd be concrete on concrete, top of, bottom of concrete column on top of concrete without bit felt. Well, that wasn't the way it was constructed. So we made a determination. The risk here is you could literally fracture those bars, because that's the only thing that's holding the whole weight of that concrete, not only the pier, but the whole superstructure. And so we decided we need to make a modification, and so we went in and we essentially made a little collar to help grab all of the things. And so a concrete collar was added around the base of the column, and sure it doesn't move, and we have not had any issues. But it's just a reminder, sometimes there's odd details. This is by no means a detail that we see very often. But if there's something that you're wondering about, it's a perfect time to give a call, give the regional guys a call, help you out, and understand what is this supposed to be. Circular column forms can be used in many ways. It can be used to form up columns, or this next picture shows use it to form up. In this case, it was a circular configuration, much like our pier actually on 27138. They could have perhaps formed that end of the pier with something similar to this. Proprietary forms that get used. So here is an example of using a column. These are some panels. If you have really oddball configurations like this, it would not be good on an exposed surface, but it is something that it could be used where it's unexposed. So I had mentioned about the snap ties, so these are again called snap ties. These little things are an inch, so our specs require that they be able to remove these within an inch. So the little weakened plane is right here, the form would be here, surface of concrete. But then this little cone would be filled after the concrete cures and hardens. So the specs require that, and it's 2401.3B1B. 3B1B, so it's on page 346 of your spec. Bottom of, so middle of the page, bottom of B1B. Says use a device removal to a depth of at least 1 inch from the concrete face without spalling or damaging the concrete. So this is the kind of product that typically gets used. There's just some wedges that have one up on the table there, some studs, ply form, things like that. You know, all things work out. So here's a picture of what it would look like, in a cut-off section. But again, this little cone then could get removed and patched. So this is again talking about that 3B1B, to remove all devices so that it has to be at least 1 inch, as shown on the bottom of this slide. And again, there's many different types of configurations, many different, this shows a 9,000 pound safe working load. That's going to come from the manufacturer's literature. So just some details of what some of the hardware might look like. So the bridge construction manual has a lot of information in it for forms and falsework. It essentially is saying the stresses must be less than allowable stresses. So that's load is less than the material that is supporting it. And deflections must be within specified limits. So among that, in our spec book, page 348, in B2C, so center of the page, it says we need to provide for these things. So we touched on this briefly earlier in the presentation. They have to control and withstand concrete pressures. They have to use standard formulas, allowable stresses. They have to figure the deflections, and they have to also consider deviations of alignment. In other words, you want to have good, solid, sound surfaces. And again, we had already talked about this, the credible information for the forms and falsework, full-scale testing we need. The deflection alignment. There's a couple different categories. If we're exposed to view, we want to be a little more critical. If we're not exposed to view, it would be something else. So this is one of the references that the spec book actually references the bridge construction manual. And so this part of the bridge construction manual in this way is our spec. So I just want you to be aware of that, and I'm going to highlight a couple of things that you might want to remember for later this week. On surfaces exposed to view, the computed deflection of any member shall not exceed 1/270th of its span or a quarter inch, whichever is less. And between fascia beams, the falsework supporting the deck is not limited to above, and that is, you can go up to a half inch. And so the overhangs have to compensate for whatever are the anticipated deflections. They must not exceed a half inch, even though it's compensated for. So those are all things that the spec book, or pardon me, the bridge construction manual talks about. So the spec references the bridge construction manual, as I said, for form tolerances. And deflection should be 121/270 or an 1/8 inch. And no offsets of sheeting or abutting the form panels. That just means if you have a big wall, you don't want to have one form platform here and then all of a sudden you have an offset of a 1/2 inch because they didn't screw something down. But here's one you might want to know. The variation from plumb or specified batter in the lining surfaces should not exceed 1/4 inch per 10 or no more than a 1/2 inch. So if you have a abutment wall that goes up 20 feet, you'd allow up to a 1/2 inch of variation from plumb. So that's just meaning we're not just going to let you pour it and it's tipping all over and you have one surface going this way and another that way. So there are some tolerances. They're in the bridge construction manual, but the spec references the bridge construction manual. So keep that one in mind. Removal of falsework. There are some requirements on page 350 of the spec. And essentially, we always want to ensure that we have full cure, and if we have post-tensioning, that we have our post-tensioning completed. So it would do us no good, like on St. Croix, we cast all kinds of concrete, we had a full box, but we hadn't post-tensioned. If we would remove that falsework, that whole thing would collapse. So we have to have our post-tensioning in place. But this is saying that you also, before you can release it, post-tensioning or no, you have to have fulfilled our concrete curing and protection plus one calendar day of dry out time. And then here's the post-tensioning piece that we talked about. So don't place loads until you've completed the curing, and determine the strength based on cylinders from the last concrete cast. So sometimes our pours get kind of lengthy. St. Croix, it wasn't uncommon to have a 10 or a 12 or 14-hour pour. And so we want to make sure that the last concrete cast has been cured at. And we want to have continuous curing. So if we remove falsework and we still need to be cured, that's right. Removal of falsework, there's some things there, 4 feet below subgrade, 2 feet channel location. And minimum curing period. So we're going to talk about this one quite a bit, but I'm going to just, for page 372, this is our first exposure to this, and you're going to be very familiar with this chart at the end. So just open your spec or find this spec, it's 2401.3-2. You're going to want to know how to find it and how to use it. And so we have the bridge element, we have bridge superstructure, slab spans, and the pier caps, and then we'll have a column for minimum curing period. So for instance, pier cap is 72 hours. So as we're looking at when we remove falsework, that's what we do. So typically our substructure elements are 72 hours, superstructure and deck are going to be a little bit. Couple questions then. Who's responsible for design of the falsework? Foreman, contractor, dredges, engineer, project engineer, or does it need to be designed if it's less than B, contractors, registered engineer. That is correct. What parts of the 2020 spec book detail falsework requirements? 2401, only, 2 only, 1 and 2 with reference to the bridge construction manual, or not in the spec book, it's only in the bridge construction manual. C would be correct. 2401 concrete, 2402 is what? Steel. Steel, very good. Okay, any questions?